Okay, so we're going to work through some Topic 2 mechanics review questions. And you can work on these on your own and just kind of watch the video as you go if you want to check your answers. So the first question says, an object of weight W is falling vertically at a constant speed in a fluid. What is the magnitude of the drag force acting on the object? Okay, so the first thing you need to know is, according to IB, weight is the force of gravity. The force of gravity on an object is the mass of the object times g, where g is the acceleration due to gravity of the object. Okay, so when it says W, it's really talking about mg. Is falling vertically at a constant speed. That's important. If it's at a constant speed, because of Newton's first law, that means that the net force is equal to 0 on the object. Sorry, F net equals 0 is what that should say, because it's in a fluid. And so what that means is we do not have free fall. And so if actually we were to draw the free body diagram for this object, we would have the force of gravity. And because we're in a fluid, we actually have not air resistance because it's not air, but we have what's called a drag force. And the drag force has to be equal in magnitude to the force of gravity. And the reason we know that, so F drag is going up, the reason we know that has to be true is because of the context clue constant speed. Okay, so what that means is F drag must equal the force of gravity in order for this to be true. The question says, what is the magnitude of the drag force acting on the object? Well, that's equal to the force of gravity, which is just the weight. And so the answer here is going to be C. Okay, so that's question number 1. Alright, let's move on. Question number 2. Question number 2 says, an object initially at rest is accelerated by a constant force. Which graphs show the variation with time t of the kinetic energy and the variation with time t of the speed of the object? Okay, so let's see. It's initially at rest, meaning that the initial kinetic energy should be 0, and the initial speed should also be 0, which is true for all of these graphs, so that doesn't help us too much. Is accelerated by a constant force. Okay, so what does that mean, a constant force? Well, we know that because of the second law, F net equals ma, mass times acceleration. And so an object acted on by a constant force will experience what kind of motion? Well, clearly constant acceleration, right? Constant force, constant acceleration. So what does that mean if we have constant acceleration? What's happening to our speed? It's increasing. And not only is it increasing, because all of these graphs show increasing speed, but it's increasing in a specific way. Now remember, for a speed time graph, the slope of a speed time graph tells you gives you the magnitude of the acceleration. So what that means is, because we know the acceleration is constant, right, we want a speed time graph that has a constant slope. A constant slope is a line. So that takes out B and it takes out D, because you can see here these are not lines, these are kind of parabolic in shape. So it can't be B or D. And now what about kinetic energy? Well, so we know that the speed is increasing at a constant rate, right? So what's happening to the kinetic energy? Well, kinetic energy is equal to 1/2 mv squared. So if the speed is increasing, the kinetic energy is increasing. Well, that's not, specific enough. As the speed increases, let's say the speed doubles, because this is being squared in the equation, right, the kinetic energy is actually going to quadruple. And so we don't have a linear relationship here. We actually have a quadratic relationship. Right? Something squared, if you graph it, you get a quadratic, you get a parabola. So here the answer is going to be A. Right? We can see the little parabola there. It's definitely increasing faster than it would if it was just a linear function. So that's question 2. I'll pause for a moment. Alright, question 3. It says, two stationary objects of mass 1 kilogram and 2 kilogram are connected by a thread and suspended from a spring, as shown in the picture. The thread is cut. Immediately after the cut, what are the magnitudes of the accelerations of the objects in terms of the acceleration due to gravity, g? Okay, so this is going to require some conceptual stuff. Really, based off of what we're being asked, the acceleration of two objects, what we should start with is Newton's second law, F net equals ma, right? Let's do that for both objects. So, second law, F net equals ma. We're going to do that for object 1. Let's say the 1 kilogram object, and for object 2, let's say the 2 kilogram object. So for 1, what does our free body diagram look like? Well, there's 3 forces on this object, okay? There is the force of gravity, let's say Fg1. There is the force from the spring pulling it up, let's say F spring. And then there's the force from the thread that's clearly going down. Okay, so we've got 2 forces going down. Let's say F thread. And what else do we know? Well, if it's suspended, that's a context clue that the net force is equal to 0. Okay, and so if we were to write that out, we would get, let's see, let's make F spring positive. Let's say the other 2 forces are negative. F thread minus Fg1 equals 0. Now, how do I know to do this? Well, I'm just following the context clues. The context clues of talking about acceleration leads me to the second law, and then this context clue suspended leads me to know that the net force is equal to 0. And so all I do is write out what I know. There's no magic behind this. It's just follow the context clues and understand the concepts involved. All right. So I've done this for object 1. Now let me do it for object 2. Object 2, force of gravity on it, right? Fg2. And what else is touching object 2? Well, just the thread. Okay, so F thread. So let's look at the actual question. The thread is cut. Immediately after the cut, what are the magnitudes of the accelerations of the objects in terms of the acceleration due to gravity? So we cut the thread. FTH is gone. What is the force on object 2? Okay, so before it's cut, we have FTH minus FG2 equals 0. This is all before the cut. What happens after the cut? This FTH goes away. And let's see what we have. We have the spring force minus Fg1. Fg1 would just be 1 times g, right? Mass times acceleration due to gravity, 1 times g. So I'm going to say minus g equals 1a. And for object 2, we cut the thread. This force goes away. We have minus Fg2 would be 2 times g. So I'm going to say minus 2g equals ma. 2, mass of 2 for object 2a. And so what I see here is, ignoring the minus sign, the acceleration of object 2 is going to be g. So that means it's either a or b that I can eliminate. And what about the other object? Well, let's see. I want to know, what is a? SP minus g equals 1a. Okay, how do I find a? Well, the thing is, immediately after the thread is cut, the spring force hasn't had time to change yet. So what was the spring force before the thread was cut? Well, let's see. Up here, the spring force had to balance out the force of gravity, which was g, right, mg, 1 times g, plus the force from the thread before it was cut, which from this equation down here was balancing out the force of gravity for object 2. That means before the thread was cut, it had to have a force of 2g. Okay, and so the spring not only had to fight against the 1g force from the force of gravity of its own weight, but it also had to fight against this thread pulling it down. So before the thread is cut, spring has a force of 3g. After it's cut, immediately after the cut, the force from the spring is still 3g. Right? Just because you cut the thread, the spring doesn't know that its force is supposed to change instantaneously. Right? So when you cut the thread, the force is still 3g. So we have 3g minus g equals 1a for object 1. So a is 2g. The answer is D. So kind of a tricky problem, but I'll pause it for a moment so you can look over that. Okay, moving on. Object 4. Problem 4, a student of weight 600 newtons climbs a vertical ladder 6 meters tall in a time of 8 seconds. What is the power developed by the student against gravity? Okay, so what do we know about power? Power is the rate. Let me erase this. Power is the rate at which work is done on an object. Okay, so power is the rate at which work is done on an object over time. How much work then does the student do when he climbs the ladder? Because we know what the time is, it's 8 seconds, but how much work does he do? What force does he have to exert? Right, remember, work is done by force, Fs cosine theta. What force is he exerting? Well, he's exerting a force against his own weight, which is 600 newtons, right? 600 newtons over a displacement of 6 meters. 600 times 6 times cosine of 0 is equal to 3,600 joules, and that's over 8 seconds. So P equals 3,600 over 8 seconds. And remember, you can't use a calculator on the multiple choice, but you can kind of reduce this out to 18 over 4. That would be 900 over 2. That would be 450. So the answer would be D. Okay, I'll pause there. And now let's move on. Question 5. Two objects M1 and M2 approach each other along a straight line with speeds V1 and V2 as shown. The objects collide and stick together. What is the total change of linear momentum of the objects as a result of the collision? Now, this is kind of a trick question, because when the two objects collide, their individual momenta will change. However, during any collision, the total momentum of the system must remain constant. That's called the conservation of momentum. So the total change of momentum as a result of the collision is going to be 0. Right? Even though the individual objects change their momenta, when you combine their momenta, the overall effect is that there's no overall change. Okay, so the answer there is D. Now, question 6. A student draws a graph to show the variation with time t of the acceleration a of an object. What can the student deduce from this graph only, and what quantity from the graph is used to make this deduction? So, acceleration time graph. Remember that that for an acceleration time graph, the slope is essentially meaningless. Right? The slope of any graph tells you the rate of change for that quantity, and the rate of change of acceleration, at least at this level of physics, is meaningless to us. So the slope of this graph is going to be mean nothing. The area under this graph, the area under an acceleration time graph, gives us the change in velocity of an object. And so, looking at our answer choices, the answer is going to be B. Deduction, change in velocity, quantity used, the area under the line. Okay, so the answer is going to be B for number 6. Question 7. A stone is falling at a constant velocity vertically down a tube filled with oil. Which of the following statements about the energy changes of the stone during its motion are correct? So, context clues. Number 1, constant velocity. Right, that's a context clue, basically telling us that, I'm going to erase that. That's a context clue that tells us that the net force on the object is 0, right? And so the reason for that is because it's not in free fall, there's actually oil in the tube. Okay, so we have a resistive force. Now, let's see the answer choices. The gain in kinetic energy is less than the loss in gravitational potential energy. Okay, in other words, is it true that the stone, as it falls, ends up with less potential energy at the bottom, or sorry, less kinetic energy at the bottom than it had in potential energy at the top? And the answer is yes, because as it falls, right, it loses energy because there's a resistive force. There's oil. Mechanical energy is not conserved. Right, so 1 is true. Okay, the gain in kinetic energy is less than the loss in gravitational potential energy because some of that lost potential energy goes to work done by the oil, right? It goes to heat or whatnot. 2, the sum of kinetic and gravitational potential energy of the stone is constant. The sum of kinetic and potential energy is just mechanical energy, and we should know that mechanical energy is only conserved in situations where there's no resistive forces. That's not true in this case, and so this is not true. And 3, the work done by the force of gravity has the same magnitude as the work done by friction. Okay, so how would we figure that out? What forces are acting on the stone? If we draw a free body diagram for the stone, there's only 2 forces, right? There's Fg, and then there's a resistive force from the oil. Okay, what do we know about work? The work done by force is Fs cosine theta. Okay, so the work done by force of gravity has the same magnitude as the work done by friction. Well, the displacement would be the same. The only way the magnitude would be the same if we knew for sure that the forces had the same magnitude. Do we know that? Yeah, we do actually. Because it's falling at a constant velocity, we know that these 2 forces must be balanced because of Newton's laws, right? And so F oil must be equal in magnitude to Fg. And so if they have the same magnitude of force and the same displacement, then they'll have the same work done. And so 3 is true. So 1 and 3 are true. That means that B is the correct answer. Okay, take a moment to look at that. Okay, question 8. An object is at rest at time t equals 0. The variation with t of the acceleration a of the object is shown from t equals 0 to t equals 20 seconds. So another acceleration time graph. Really, we've done this already. You should know, though, that for an acceleration time graph, the area under the graph tells you only the change in velocity. Okay, so for this type of graph, the area is equal to delta V. All right, if we go back up, we'll see that the object starts at rest. All right, so that's important to keep in mind. What is the area here? Or I should say, it says what is the speed of the object when t equals 15 seconds. So that means we need the area from 0, where it was at rest, up to 15 seconds. Okay. So that area, we've got a rectangle here. That's a 5 by 5, so that's 25 from the rectangle. And the triangle, 1/2 base times height, so that's going to be 10 times 5 divided by 2 is another 25. And so the area under the graph is 50 meters per second. Okay, that's not the speed, but that's the change in speed. But then again, if you start from rest and your speed changes by 50, how fast are you moving? You're moving 50 meters per second. So the answer is B. Keep in mind, you could have the exact same graph and if you started at t equals 0, let's say you were moving 25 meters per second at t equals 0 with the exact same graph, that would have made the answer C. Okay, so keep in mind the area under the graph, all that tells you is the change in quantity, not the actual quantity itself. Okay, I'll pause for a moment. Okay. 9, which of the following is proportional to the net external force acting on a body? This goes back to Newton's law, Newton's second law, F net equals ma, and a is the rate at which the velocity of an object changes over time. That's how acceleration is defined. So delta v over delta t, rate of change of velocity. So the answer is D. Okay, so those are the multiple choice questions, and I will make another video for the free response question. It's kind of a lengthy question, so I want to make sure that has a separate video.